Hi guys, today I want to share to you all on how to manually calculate building calculation using ASHRAE CLTD, SCL, CLF method and example. As you know that CLTD is a cooling load temperature difference, SCL is a solar cooling load, CLF is a cooling load factor. So those three is a very important parameter to calculate building manual calculation if we are using ASHRAE CLTD, CSL, CLF method. Okay, let's start with it. Okay, as you can see, this is a example of the problem. Okay, to do this, to answer this problem, you need to refer the 1997 ASHRAE Handbook Fundamentals for IP unit. As you can see, this is a layout of the classroom. This classroom consists of other room partition. Only the east side wall of the classroom were exposed to the outdoor environment. The other west, north and south side are enclosed space, in which this partition is not exposed to the outdoor air. Okay, this classroom is 20 feet long, 20 feet wide, and 10 feet high. There are also 8 feet times 30 feet window in the east wall. Only the east wall is the exterior, which is contact with the outdoor surface or outdoor air. So we assume that thermal condition in adjacent space for the west, south, north, above and below are the same as those in the classroom because there's no contact to the outdoor air or outdoor temperature. The question is, we have to determine the cooling load at 9 AM and 12 noon on July 21st. Okay, this is the question for this problem. Okay, other condition that also we mentioned is latitude of the location is 40 degree north. The ground reflectance 0.2. Clear sky with a cleanliness numbers 1.0. Overall window heat transmission coefficient. There is a U value of the window. U value. The U value of the window is 0.55 BTU per hour feet square Fahrenheit. Okay, so room dry bulb temperature is about 78 Fahrenheit and the humidity is 50%, while outdoor dry bulb temperature is 66 Fahrenheit at 9 AM and 86 Fahrenheit at 12 noon. This is outdoor dry bulb condition. Okay, while outdoor RH is 60% at 9 AM and 51% at 12 noon. For the schedule of occupancy, the class has been made for 20 people. That is 20 people student in the class, that they will enter the class at 9 AM and stay for 8 hours. So this is for 8 hours class, 8 hour class, and the class will begin at 9 AM. For the lighting schedule, we use the 300 watt of lamp, and also for 8 hours, starting the class at 8 AM in the morning. For the exterior wall structure, we can refer to the chapter 28, 1997 ASHRAE Fundamental. As you can see, the layer of the wall, for example, this is the east wall east connected wall, east facing wall for this classroom. So there are a layer of AO, outside surface, A2 face brick, B3 insulation, concrete block, C3, and inside is EO, inside surface. So this is a five layer of the wall that facing east. And then we have the exterior window. Just now I mentioned the U value of the window is about 0.55 BTU per hour feet square Fahrenheit. And then the window is a single glazing window, okay, with no exterior shading at all, no shading. So the XC we assume that 1.0 solar shading coefficient. And for the floor is covered with the carpet. Inside wall partition is made of gypsum. Okay, this is all those condition that we need to take care of about for cooling load calculation. Okay, first of all, we start from the cooling load due to the exterior wall. So how to calculate the cooling load due to the exterior wall? Okay, remember, we calculate only the wall that facing outside surface, meaning that for this class, only for the building of the class, only the east surface wall facing the outdoor surface, outdoor condition, that is outdoor temperature. As we can see, the wall is built in 1, 2, 3, 4, 5 layer. Okay, this layer AO, A2, B3, C3, EO, you can refer to the ASHRAE. Okay, let me show you. As you can see, table O4 consists of one layers thermal resistant that can be see at this table 11 chapter 29 ASHRAE 1997 fundamental. So these R value for all those layers can be get at the table 11 chapter 28 1997 ASHRAE fundamental. Okay, you can see that AO, outside surface resistance, the one that I will highlight, AO, so the resistance is 0.33 feet square Fahrenheit hour per BTU. Then goes to the A2 for inch face brick, the resistance is 0.43, followed by B3 insulation 6.67 resistance, C3 heavyweight concrete block, the resistance is 0.71, and lastly EO inside surface resistance, the resistance is 0.69. Okay, those to get the U value, you must get the total R value first. So the total of the resistance, the R value is 8.83 feet square Fahrenheit hour per BTU. Now we can get the U value, that is the thermal transmittance of the wall, is about 1 over R, 1 divided by resistance, 1 over 8.83, then we can get 0.113 BTU per hour feet square Fahrenheit. This is the thermal transmittance value for the wall. Okay, or we highlight it. From the table 33 of the handbook, we can get what is this wall type. The wall that facing east just now, what is its wall type? So, we refer to the ASHRAE 1997 Fundamental, table 33A. First, we must see what is the principal wall material. For this principal wall is the wall that is located inside of the building. In this case, it is a C3 concrete block. So we highlighted the C3. Okay. While secondary materials is face brick, the material that facing outside surface. A2 face brick, you can see. So the intersection of this C3 and face brick is, we know that it's all around here. But then we have to determine the total resistance of the wall. The one that we just got before is around, see, you have to see this, refer to the R value of the wall, total R value of the wall. Our case is 8.83. So according to here, the ratio of the principal wall to the secondary wall, the R resistance value is around 7.75 to 9, because our value is 8.83. In this case, our wall type is this type 13. See, this is how they got type 13 wall. Then, from the table 32 of the handbook, we can get the CLTD. We must look, we go for the table 32. We want to look at the CLTD, cooling load temperature difference. At 9 p.m. and 12 noon for the east wall. Okay, so we go for the table 32. Okay, so 33, go for table 32. Okay, this is table 32. And just now we know this wall number, wall type is the type 13. So that we refer at this wall number 13. And then remember that we want to know the July cooling load temperature difference. So of course we have to use this table, because we know that we are looking for the July July cooling load at July, at month of July, and the time is at 9 and 12 noon, 9 a.m. in the morning and 12 noon. So facing east wall at 9 a.m. the CLTD is 16, while 12 noon the CLTD is 25. So this is how they got CLTD 9 and CLTD 12. The CLTD corrected is not needed because these ASHRAE are intended to do at 40 degree north and on July 21st. So this is happened on July 21st. So this is the reference. So when the location is at the reference, we don't need to do the CLTD corrected. But let's say we want to do in Malaysia, so of course this longitude latitude is not the same like this 40 degree north latitude. So we have to do the CLTD corrected if in case of we want to do it in Malaysia. So let's calculate at the moment, let's calculate this cooling load for the wall. Cooling load due to the exterior wall. So the Q equal to, we have know the U value, thermal transmittance of the wall, and the area of the wall, and we must times the CLTD 2 times. This one is at 9 AM and another one Q at 12 noon. The U value is the same because the same wall application, and the CLTD is at 9 AM, CLTD at 12 PM noon. Okay, then for this we know that the U value is the 0.113 BTU hour feet square Fahrenheit. Okay, we know that. And then the area, we just know that it's a 20 feet tall. Okay, times 20 feet length wide, then 10 feet tall. But this we must minus with the window area, because we just want the opaque surface of the wall. We don't want to consider yet the window area. So the area, okay, we get the area, and in feet square, then we time with the CLTD at 9 PM and 9 AM is 16. Then another case, we apply at, still U value is 0.113. So the area that we got here, okay, same surface, but only this CLTD we use 25 because CLTD cooling load temperature at 12 noon. So the answer is here for cooling load due to the exterior wall at 9 AM is 173.6 BTU per hour, while cooling load due to the exterior wall at 12 noon is 2.71.2 BTU per hour. Okay. Now, we just got the value of cooling load due to the wall. But now we see that the wall that facing east, for example, this is the drawing of the wall. So we just calculate just now the wall area of the cooling load. Now we have to calculate the window conduction. So we want to know the heat load to the window. So now we have to look at this table 34 ASHRAE. Go for table 34. Okay, now we see the table 34. We are interested at the CLTD 9 AM and CLTD 12 noon. So if you can see the conduction through glass here, the CLTD at 9 is 2 Fahrenheit, and CLTD at 12 is 9 Fahrenheit. So just pick this number, while the CLTD collector is not needed, as I mentioned before. So we just calculate the cooling load through the windows. Same goes to this situation that we have to get this Q at 9 a.m., which is this one, and cooling load at the 12 p.m., which is this one. So, but this one we have to know, we have to consider the U value of the wall. Okay, so we need Q equal to U value. I write it again. Q equal to U of the wall, U value of the wall, and then we have to times the area of the wall, and we have to times the CLTD. Two condition. One is at 9 a.m. and another one Q at 12 p.m. U value of the wall. Okay, so the CLTD is at 12 p.m. CLTD at 9 a.m. So the U value of the wall is this one. Zero 0.45 BTU per hour, feet square Fahrenheit. Then we must times this area of the window only. 8 times 13 feet square. Okay. Right. And then we can get this, the Q cooling load through the window conduction is at 114.4 BTU per hour, and at 12 p.m. 514.8 BTU per hour. Okay, so now we have this two value of cooling load already. One is the cooling load to the exterior wall at 9 and 12 p.m. and cooling load to the window conduction at 9 and 12 p.m. Okay, then, as you know, the heat transfer to the window is not just from the conductivity, from the conduction. It's because the heat source from the light, from the sun, is not only from the radiation, but also from the light itself. There are heat. So we have to get this solar load through glass. Okay, solar load through glass. And how to get that? We refer to table 35B of ASHRAE 1997. Okay, zone type for use with SCL and CLF table. So we want to do the solar cooling load. Okay, from table 35B, type for glass, we have to know the type of glass first. So how do we know that? They mention this type for solar glass is A. Okay, remember that just now our situation is like this. Number of wall is 1. Okay, floor covering, what type of floor that we use? Just now mentioned on we use carpet. Okay, carpet covered by floor. And other partition type is a gypsum. Okay, so how about the inside shade? Inside shade is this, we don't use any kind of what we call that, curtain, inside curtain. So it is in category B, no inside curtain at all. Okay, so our glass, based on those type, our glass solar is in type A. Okay, that's why we get the glass solar is A. Okay, from table 36, okay, we know that, for table 35, we know that our glass solar is A. Then we go for table 36. Table 36. Go for table 36. So it's 38 already. Wait, looking for table 36. Okay, for table 36, just now, yeah. For table 36, for zone type A, table 36, on July, the solar cooling load for the 40 knots latitude, we can see that solar cooling load at 9 AM is still glass facing east. At 9, the SCL is 183, while at 12 noon, the SCL is, solar cooling load is 67. So, from here, we can calculate the cooling load through solar load, cooling solar load through glass. So, Q, same goes to the Q at 9. Here is, make it bigger, is Q at 9 AM, is Q at 12 PM. So, we use the shading coefficient of 1 because there's no any shading that will apply. So, we assume that 100% of direct sunlight will coming to the window, and the solar cooling load we refer to the ASHRAE table for 183 at 9 AM. Then the cooling load will be 19032 BTU per hour at 9 and 6968 BTU per hour at 12 PM, 12 noon. Okay. Okay. How about the cooling load from partition, ceiling or floor? Remember that the partition, ceiling and floor were not exposed directly towards the outdoor condition, outdoor air. So, 0 BTU hour we are consuming because thermal condition energy space is the same as the classroom. Okay, there are no direct heat transfer happen here. Okay. Okay. And then, we must consider on heat from the cooling load from the people. Okay. From table 35B, we can get the zone type for people is B. So just now, we gather class A for this wall, SCL, solar cooling load. But now, how about the people? So the people, we have to refer table 35B. Okay. Okay. So just now we get glass solar is type A, but the people and equipment we are fall under type B. Okay. So from the table 3, for seated very light work, the sensible and latent heat are as follow. Now, when we got the type people, then we have to go for table 3. We have to refer table 3. Okay. Table 3 is the rate of heat gain from occupant of conditioned space. This is will be used only at the conditioned space. Okay. The situation is seated very light work. Okay. The student in the classroom all are seated and doing very light work like writing and etc. So this is applicable for office, hotel and etc. So we can see the sensible heat BTU for this activity are 245 BTU per hour, while latent heat is 555 BTU per hour. So this is a people sensitivity, people latent. Okay. We know that we can calculate the cooling load from people. Okay. Okay, after that we have to go from table from table 37 for zone type B and 8 hours. Okay. So we want to know we know that the people seated doing the very light activity for about 8 hours in this classroom. So we want to know the CLF, cooling load factor. To know the cooling load factor, we have to refer the table 37. Okay. Table 37. Okay. Table 37, we know that our people is in zone type B. So how to refer the table? Okay, number of hours after entry into space or equipment turn on. We can see that hour in space, the student must be in space for the zone type B is about 8 hours. What we know that. Then the student enter the space is around 8 in the morning. So we want the exact 8 a.m. in the morning, but we want the hour in space is about 8 hours. Then the first hour in the room will be 0.665 because we know the student enter the room at 8 a.m. So 1 hour after 8 a.m. is 9 a.m. So 9 a.m. is 0.65 CLF. Okay. How about if the question asks for at 10 a.m.? The 10 a.m. will be CLF will be 0.75. And what about 11 a.m.? 11 a.m. will be 0.81. And in this case, we want to know at 12 noon is 0.85. So both 0.6 at 9 a.m., 0.85 at 12 noon is the CLF for this room, cooling load factor. Okay, so we got 0.665 and 0.85. Now we can put the information in this Q sensible and Q latent. So as the Q sensible, at 9 is 3185 BTU per hour. At 12 is 4165 BTU per hour. Okay, so we have to put in the formula Q latent is n number of people equal to 20 times 155, okay, equal to 3,800 BTU per hour. The Q latent for people is the same at 9 and 12 noon because it's the same person at all in the room. It's not changing the amount of the people. So we assume that it's not different. Only the Q sensible have 9 and 12, 9 a.m. and 12 noon. Okay. Alright. Continue for the heat load from lighting. How to get the heat load from lighting in the class? From table 35B, we still have to determine the zone type for lighting. Okay. So the zone for lighting, as we can see, just continue from this just now, table 35B. Zone type for you with SCL and CLF table for the single story building. We got for the light, we in the zone type B. So then we have to go for table 38 for zone type B, 8 hours on. Okay. Table 38. Okay, so go for the cooling load factor for light. This is zone type B, and then 8 hours operation. So as I mentioned, 1 hours after 8, if the CLF is 0.75, yet there is at 9 a.m. and 10 a.m. 0.85, 11 a.m. 0.90, while 12 noon is 0.93. So this is how they got CLF at 1 hour, during 1 hour. At 9 is 0.75, at 12 after 4 hours is 0.93. The formula is that use FUL equal to 1, assuming FSA equal to 1. Okay, this FUL is and FSL is only a factor. A factor meaning that how frequently we operate this lighting. But for those light, for the FUL is like a ballast factor, but the FSCL is like how frequent we open the lamp. In this case, we open the lamp throughout the day for about 8 hours and we close at night. So the FSA will assume 1, and there's a ballast factor also 1. So for this cooling load calculation, we can see that we can use that. If you remember that this 3.41 is the constant, while watt W is a watt of the lamp. The lamp energy, the one power consumption is 300 watt altogether. Then we times with this FUL, FCA and CLF at 9 a.m. and 12 a.m. So at 9 a.m. the BTU, the cooling load for the lamp is 767.25 BTU per hour, while at 12 noon is 951.39 BTU per hour. Okay. So how about the cooling load from the appliances? Okay, of course we know that there's no mention any appliance at all in this room so far. So in this problem, so we assume that the cooling load from the appliance is 0. But if in case there's an appliance, yes, you have to calculate for the appliance. Okay. Last but not least, we have to calculate the cooling load that occurs from the ventilation. As we know, in the air conditioning space, we assume that there still be a infiltration, ventilation or infiltration. Infiltration will occur. Infiltration will occur. Let's say there is a small gap opening on the doors or the windows. There still will be a what we call it, infiltration of air that will coming inside. From this one we have to refer table or 3, the recommended fresh needed for classroom. So we assume that from this classroom is already needed 8 liters per second, the fresh air needed to enter the room. We allow that 8 liters per second per person because we are intended design that this room must have the 8 liters per second fresh air. Then 8 liters per second is around 70 CFM, cubic feet per minute. The flow of the air is 17 cubic feet per minute. Okay, based on this data, we can calculate the Q sensible and Q latent, because as we know that the air from outside coming to the inside, the air not only bring the sensible heat, they also have a kind of moisture content in the air. So we have to calculate also the Q, the cooling load of the latent, okay, of the latent heat. So the formula is here. The Q sensible equal to 1.1 is the constant airflow times temperature outside minus temperature inside. Okay, so for the Q sensible, we know that the 1.1 times the airflow is 17 CFM. Okay, temperature outside minus temperature inside is 66 Fahrenheit minus 78 Fahrenheit. The Q sensible at 9 AM will be negative 24.4 BTU per hour. And the Q sensible at 12 is 149.6 BTU per hour at 12 noon. Okay, it seems easy to calculate the Q sensible, but for the Q latent, we still need an extra works to calculate that. So we use this formula, Q latent equal to 4,840. This is the constant. We time by the airflow. You know that the airflow is 17 CFM, but in this case we have to times with outdoor humidity ratio minus indoor humidity ratio. Okay, so first of all we need to see the condition at 9 AM and 12 noon, the outdoor condition. That's why the question mentioned on the outdoor condition of the room at 9 AM and also at 12 noon. This we can get from this, in this real situation, we can get from the weather station data. At 9 AM, the outdoor relative humidity is 16%, while the dry bulb is 66 Fahrenheit. While at 12 noon, the outdoor relative humidity is 51%, while the dry bulb is 86 Fahrenheit. There's no other way to get the humidity ratio besides we are using psychrometric chart. So in this case, we have to use psychrometric chart to get the humidity ratio for the what we call it, for the at 9 AM and also at the 12 noon. Okay. And how? In this case, we got this humidity ratio at 9 is 0.08 pound per pound, and at 12 noon is 0.0135 pound per pound. Okay, this is what we call this humidity ratio. Okay, so for this case, for 78 Fahrenheit, this condition, 50% RH, indoor humidity ratio would be this one. Okay, 0.0102 pound per pound. Okay, in this case, we assume that Q latent at 9, based on this formula, is 4,840 times the constant times the CFM, the airflow 17 CFM. So we must to subtract this what we call humidity ratio 0.08 is okay, outside humidity ratio at 9. We have to minus the inside humidity ratio 0.0102, and then the answer is the Q latent at 9 is negative 181.0 BTU per hour, while Q latent at 12 is we use that humidity ratio outside minus the humidity ratio inside. Outside 0.0135 minus 0.0102, and the answer is 271.5 BTU hour. Okay, so in this case, we already get all humidity load from this from all the components, especially wall, window conduction, window solar, partition, people, light, appliance that we don't have the appliance and partitions. Okay, And last but not least is cooling load to the ventilation. Okay, as you can see, at 9 AM, we have to total all together this cooling load to get the cooling load at 9 AM. Cooling load to the wall is 173.6. Cooling load to windows conduction is 114.4 BTU per hour. Cooling load from solar is 19032.0 BTU per hour. North cooling load for partition. And for people, sensible plus latent, sensible 3185 plus 3100 BTU per hour. And for the light, it's 767.25. There is no appliances cooling load, because no appliances at all. For the ventilation is negative 224.4 minus 181. This is for the Q sensible. Okay, is and latent at 9. See, is and this. See, so the total cooling load for at 9 AM is 25,966.9 BTU per hour. Okay, then we total up all together also for the 12 noon BTU per hour, and we got 16,391.5 BTU per hour. Okay. Okay, this is the differences cooling load at 9 and 12 noon, as we can see. So we can assume that here we notice that the higher cooling load is needed in the morning. This counterintuitive because of we were expected high cooling load at noon. Okay, it's far from the normal. However, remember that the wall and window is facing east. The sunrise is from the east. You see, you can see that our situation is different. Our situation, only the east wall part and window are facing the outdoor condition, while the northwest and south is not facing the outside condition at all. So we assume that the sun rise from the east and set at the west, so we can see that more more east side of the wall receive sun radiation compared to the others. Okay, so the window is single glaze and no exterior shading is used. So no wonder why we get higher load in the morning compared to this afternoon load. Okay. Okay, this is important of study. In green building, is very important to study the differential load at different time, because the load is the instantaneous load is different at 9 AM different and 12 noon different. Besides, as we have mentioned before, the wall itself have experienced this thermal lag. Okay. The greater the heat capacity of the wall, they will store more the heat, and then they will release slowly, so that we can see that not just instantaneous heat transfer happen, but there also a thermal lag effect. So this is kind of a parameter that we need to study in order to get the exactly cooling load. What is exactly cooling load in our building? So to study the cooling load, we have to do manual calculation. But nowadays, we also have this software. Okay, we also have the software like Elite CHVAC, Trace 700, and so on. Okay. So that's it for today, and see you next time. Don't forget to subscribe my video and like my video. Thank you. See you again.